Hi there! We know that all matter in the universe is laid out as a network of filamentary structures popularly known as the cosmic web. We have discussed the distribution of galaxies on this cosmic web on this channel. But besides galaxies and dark matter, the cosmic web is believed to comprise low-density plasma which forms a significant fraction of the normal matter in the universe. But it is not easy to detect this low-density gas found in cosmic filaments. Now, with the second-generation instruments on board large telescopes, astronomers are employing data from these ultra-sensitive machines to detect the cosmic web directly as well as indirectly. In this episode, we'll talk about recent discoveries of cosmic filaments where astronomers applied interesting techniques to obtain these data. On the way, I'll discuss about various elements such as the cosmic web, Lyman Alpha emission, quasars, and much more to make these studies accessible to all of you. So tighten up your seatbelts and get ready to dive into the mysterious world of large-scale filaments. Let's begin. All matter in the universe lies along a web-like structure rightfully nicknamed the cosmic web. The structures on the cosmic web itself can be categorized into three distinct yet continuous environments in which galaxies can live: the clusters, filaments, and voids. While clusters of galaxies are the most studied regions of the universe, only about 10% of all galaxies are found in them, while the majority of the remaining galaxies occupy the large-scale filaments. But it's not just that. The medium that fills the large-scale filaments is likely a solution to the missing baryon problem as well. Baryons are the usual atoms and molecules, the matter that you and I are made up of. Observations of the cosmic microwave background and Big Bang nucleosynthesis studies suggest that the baryonic matter accounts for approximately 4.8% of the total energy content of the universe. However, a census of baryons in the observable universe shows that the actual observed baryonic matter accounts for less than half of that amount. In other words, there are fewer baryons emitting electromagnetic radiation than expected. This discrepancy is commonly known as the missing baryon problem. It is therefore crucial to detect the cosmic web to study what it is made up of. It is possible that the plasma permeating the large-scale filaments will help resolve the issue of the missing baryons in the universe as well. But these cosmic filaments extend several megaparsec across, and that is why astronomers began exploring them with state-of-the-art telescopes in the last few decades only. This image, for instance, shows the number of observations taken to map part of a large-scale filament feeding a distant cluster of galaxies. Each of these observations, represented by a red rectangle on the right image, took over an hour of telescope time. But given the nature of light, the problem in case of the large-scale structure is compounded. Although the angular size of the filaments at high redshift would be smaller, the galaxies as well as gas which can be used as a tracer becomes faint and eventually undetectable at higher redshift. This means that while defining a filament is an issue even with the low redshift data, reasonable progress has been made using galaxies as a tracer. For instance, the long filaments crossing the Coma supercluster, which is one of the largest structures in the nearby universe at a mere 100 megaparsec from us, have been studied using the distribution of galaxies as well as radio emission from the gas in the filament. This gas is sometimes referred to as the intrafilamentary medium. Simulations suggest that the typical density of this warm, hot intergalactic medium, popularly known as WIM, is very low. At around 1 to 10 particles per cubic meter relative to 10 to the power 25 particles per cubic meter in the Earth's atmosphere, the elusive WIM is extremely difficult to detect. Moreover, except for where the medium is denser than usual, for instance closer to the boundary of clusters of galaxies, where the distinction between the intracluster medium and the medium in the filament vanishes, the WIM is at a temperature of 100,000 to a million Kelvin, which is too warm for the UV detectors while too cold for the X-ray missions to detect it. That said, some progress has been made on that front as well. In a recent study, astronomers stacked the low-energy X-ray emission from more than 7,800 cosmic filaments identified using optical data to show a statistically significant detection. In another work, a 13 megaparsec long X-ray filament is found to connect two galaxy clusters, Abell 3667 and Abell 3651. But now, researchers are testing the boundaries of the modern instruments by exploring innovative techniques to observe these large cosmic filaments directly. In a recent study, the Multi-Unit Spectroscopic Explorer, also known as MUSE, installed on the Very Large Telescope in Chile, stared at a part of the sky for hundreds of hours. MUSE is a multi-unit spectrograph which combines the capabilities of a sensitive imager with the measuring capability of a spectrograph. Basically, it produces three-dimensional images where the third axis represents the wavelength distribution of light, in other words known as a spectrum. So each 1 square arc-minute area observed by MUSE is split into 24 channels or slits, each of which can be further divided into 48 mini-slits. This means that it is possible to take 1152 spectra, each representing a point in the 1 by 1 square arc-minute area on the sky. Astronomers use these ultra-sensitive data from MUSE to image a filament connecting two quasar host galaxies. Quasars, as we have already discussed on this channel, are a subclass of distant AGN with extremely luminous centers. They are so far away that in optical images they show up like bright stars with a faint halo around it, which may be resolved into the parent galaxy for a few of them. Quasars are believed to be a consequence of high-velocity gas spiraling into the central supermassive black hole of the host galaxy. It is incredible to think that the light which allows us to observe this piece of the cosmic web was emitted when the universe was 2 billion years old, just about 14% of its present age. This is the first time ever that such an image of the cosmic web has been obtained through direct observations. This is also the first time ever that astronomers have managed to distinguish between the medium in the filament and the circumgalactic medium surrounding the galaxies which fuels their star formation. The discovery of this incredible structure extending to a vast distance of 3 million light-years or almost 900 kiloparsec has opened up new avenues to detect and study how gas flows in the cosmic web and its impact on the growth of galaxies fueled by it. In another instance, an international team of astronomers detected a different cosmic filament via absorption of Lyman Alpha photons emitted by a background quasar. As discussed in our episode on spectra, Lyman Alpha emission line is produced at a wavelength of around 1215 angstrom when the electron in the neutral hydrogen atom jumps from the n is equal to 2, that is the first excited state, to the ground state. Quasars are common sources of Lyman Alpha emission due to the presence of excited gas in the vicinity of their central supermassive black hole. But in the context of this study, this emission became a tracer of the cosmic web because the Lyman Alpha photons were absorbed by the plasma in the filament which lies along the same line of sight in front of it. This filament is a specimen of a special class of objects called the partial Lyman limit systems or PLLS. These objects are large nebulae of gas often observed around distant quasars, where the neutral hydrogen gas density is high enough to partially block the Lyman continuum radiation, but not completely opaque like a full Lyman limit system. But it is not just that. Using the high-resolution MUSE data, astronomers also identified 7 Lyman Alpha-emitting galaxies and a Lyman Alpha-emitting nebula in close proximity and almost linear projected configuration around this system. A Lyman Alpha-emitting galaxy is a type of distant galaxy detected via its Lyman Alpha emission. Since light has a finite velocity, these young galaxies offer a glimpse into the early universe. At a mass of 100 to 10,000 million solar masses and an estimated age of just 200 to 600 billion years, Lyman Alpha emitters are crucial for advancing our understanding of growth of Milky Way-like galaxies. In the context of this study, though, it is interesting that none of the Lyman Alpha emitting galaxies exhibit quasar-like features, therefore making this discovery quite unique. The backlit gas in the 11.7 billion year old nebula extending to a physical size of 260 kiloparsec has a metallicity 10,000 times lower than the solar neighborhood and particle density which is 100 billion trillion times less than our atmosphere. Metallicity is the fraction of elements heavier than hydrogen and is often quantified in units of solar metallicity. These results have led astronomers to conclude that the glowing nebula associated with the Lyman Alpha emitters is part of the cosmic web hosting pristine gas which will eventually flow into the observed Lyman Alpha emitters and other galaxies in its vicinity. I hope you enjoyed this summary of recent results on the detection of cosmic filaments. If so, please do share our content with other astronomy enthusiasts and don't forget to like, share and subscribe to our channel. We always look forward to your feedback, so do let us know your thoughts in the comment section below. I will see you next week with another interesting topic in astronomy. Until then, take care.